Test it, like 1, 2, 3. Is it working or? Yes. Yes. Okay. Okay. So what? Okay. We can wait if you... We're on.
Good morning, everyone. It's a pleasure to have Tomasz Idziaszek here for this second week of our summer school. I hope you enjoyed this week, and thank you, Tomasz, for being with us. And thank you again.
Thank you for having me once again, because I have a pleasure of being here 3 years ago. Okay, so my name is Tomasz Idziaszek, and I'm from Poland, from Warsaw University. Nowadays, mostly I do a lot of stuff around programming competitions on the high school level and on the students level. I'm organizing competitions. I write books about programming competitions, about solving tasks. Thank you. Okay, so we will be doing contests, and the tasks from the contests will be from the Polish competitions. So I think they will be quite challenging, but I think it's like the best thing to if you want to learn, you have to like practice challenging problems. We will have, I think, 4 contests consisting of 10 to 12 tasks, and these will be team contests. And I think on the last day, on the Saturday, we will try to do something different. Probably, if we will do something like that, if you will have some additional questions, or you want to practice specific problems from the previous contest, then we'll have like this questions and answers session. We'll see how this will work out. Okay, and usually the schedule will be as follows. We'll have lectures at 8:30 every day, and apart from today, the lectures will consist mostly of me talking about the problems from the previous competition. And today will be different because we still don't have any competitions. So today I will be talking about knapsack problems. So yeah, so dynamic programming and stuff. One more thing, I thank you for everybody who fill out the survey I sent about what topics you would like to hear. I tried to like select the tasks which fit your preferences. I think that in the previous week you have lectures about flows. Yes. Okay, so that thing will be not covering in depth. So yeah, so we will try different topics. Okay, so I think we can start. So let me try. Okay, knapsack problem. I think most of you are familiar with this, at least with one version of this problem. We will try here to show the different versions and how to solve different variants of this problem. So, like the one of the simplest formulations is as follows: we have some items, and these items have certain weights or sizes, you can say. So have n items, and each item has its size or weight. We will denote it by W1 to Wn, and these are weights or sizes of items. And you also have a knapsack which has a certain limit of weight. Okay, and the task is you want to select a subset of items which will fit the limit of weight, but which will be as big as possible. So, for instance, if we have like 3 items and with weights 1, 2, and okay, let's take it 5. And if we have like a knapsack of size of 7, so here we can take two items of size 2 and 5, and then they will fit into this bag. So the optimal solution would be to take 2 and to take 5. Of course, you can have additional solutions, but they won't be optimal in the sense that the total weight of items which we choose is less than 7, which is maximal here. So you can like take 1 item of each kind, and also you can take 1 and 5. But you cannot take 1 and 2. You can take 1 and 2, but you cannot take everything 1 to 5 because the size would be too big. It will be 8, and like the limit is 7. Okay, and what about if we have the knapsack of size 6? What can we take? If we want to take, yes, we can take 1 and 5, and this will be also maximal. And what if we have limit of 4? Which items we can take? 1 and 2. So then the total size will be 3. This is less than 4, but we cannot make any subset with total weight equal to 3, equal to 4. Okay, so this is like the basic formulation. And to solve this problem, we use the standard dynamic programming. So okay, we can use the dynamic programming by putting the items into the knapsack one after another. So we can think about it this way. We will have an array ij. And this will be our array in dynamic programming, and this will mean okay, what is the maximal size we can put in our bag if we consider items from 1 to I, and we have enough room of size j. So actually, we will be our sub-problems will be on 2 dimensions. One dimension will be the number of items we are considering, and the second dimension will be the limit of weight, and we will be considering the limits from 0 to m. So this will be what is the maximal subset Maximal in the sense that we are calculating the sum of weights of items. If we consider items from 1 to I, and we have and the space is limited by J. Okay. Okay, and as usual in dynamic programming, we need to tackle two things here. First, like we need to have a general recurrence. So how this value is computed from the values with smaller i's and j's. And the second thing, what are the boundary conditions? Okay, so let's write a general recurrence. Okay, so we are considering two cases here. We would like to, so we are considering items from 1 to I, and let's take the last item number I. So we have two possibilities. Either this item is not taken into the subset, or this item is taken. If item I is not taken into the subset, this is the same as so this is the same as if we consider items from 1 to I minus 1. And the space is stays the same because we didn't put anything more into the bug. So we will have. So this is the maximal subset if we choose not to take the item number I. Okay, and so what if we take it? So first of all, we know that if we take item I, it must fit into the bug. We will have enough room of J. So first of all, we need to check whether the size of this item is actually the item is not bigger than J. Because if it's bigger than J, then we cannot put it. So the second case will be only if the size of the item I is less or equal from J. Okay, and what happens then? Then we need to consider other items. So items from 1 to I minus 1. So we need to find the maximal subset from these elements. And what is the space left in our bug? It's J minus Wi because we use Wi for item I. Okay, and these are two cases which we have to consider, and we will take them the case which will give us the maximum value. So we will take its maximum from these two cases. Of course, the second case is only valid if this inequality holds. Okay, so this is the main recurrence equation, and what are the boundary conditions? So so the boundary conditions are because we see that the first dimension is getting smaller when we are calculating the recurrence. The second dimension is also getting smaller. So the boundary conditions are when we get to like to the lowest possible values of I and j. Here the lowest possible values will be 0. So we can consider what's happened if we what is happening if we have 0 items. Because if I is equal to 0, this set is actually empty. So we didn't consider any items for our bug. So actually, if you have 0 items and any kind of bug, what is the maximal size we can put in the bug? Well, it's 0. If we don't have any if we don't have any if we don't have any items. Okay, and what if we have some items? And we have an empty knapsack. Well, it's also 0 because we cannot put anything. Of course, we need to have these assumptions that the weights are positive, but it's kind of sensible. Okay, so it will almost work, but still we need some. Okay, still we need some change, because if we calculate this recurrence, every value will be 0. Yes. Okay, because we initiated it with zeros, and here we only take the values which are smaller. Okay, so where's the error here?
That's the date you have one
Yeah. Okay. So actually here we need to add the weight of the item we'll be considering. Okay. So okay. That's better? Okay. Actually, we can change a little. We can change this the meaning of this. Okay. Yeah, actually, yes. Actually, this is a good catch. So, or is it? Because if we can we have a 0 here? if wi is equal to j, so we have like perfect fit. So then this number will be 0. So we need this case. Okay, so let's say that we have one item of. So the question was, do we need this? Do we need this last line? So let's say that we have item of size 5, and we need to calculate d15. Okay, so then from the this okay, so from this relation it will go to this one definitely. Okay, so let's say that we have one. So 2 is 5, 1 is 1, and we need to calculate 2 and 5. Okay, so what is the max here? We will be calculating d1 and 5, yes, and we will be calculating d1 and 0 plus 5, and w2 is equal to 5 and is less or equal than 5. Then this if is also correct. So we will go to the case when the second dimension is 0. Yes. Okay, so we're telling that, okay, this is not necessarily because we can go with our recurrence once again. Okay. Yeah. Okay. Yeah, you convinced me. But it's like, but it's okay if we put it like this. Okay. But we can also change this the meaning of this Ri a little bit, because if we can just say whether we can we don't need to put the maximal subset, because we can say, okay, because we still considering all of the space from 0 to m, so we can just ask whether we can actually fit the items which will take exactly space j. So another formulation will be, what can we take a subset from considering items from 1 to I and fill the space of j. So let me rephrase it. So we consider items from 1 to j, and so can we fill space of size exactly j if we consider items from 1 to I. Okay, so what will change in our recurrence? So the first change will be that the type of this array will be booleans. So we only put it here true or false, but we can also apply the standard conventions that if we put 1, it means true, and if we put 0, it means false. Okay, so we assume that this is these are booleans, so we don't need to put here any addition. So actually, if we know that we can put elements from 1 to I minus 1, which fill exactly size j, then this is okay. Otherwise, we try to put another element I, and this is also okay. So actually, this max is like OR. Yes, if this is true or this is true, then the whole case is true. But also max will work because it's like if we apply this convention that 0 means false and 1 means true, then if we take the maximum, then this is exactly what is happening when we take OR. Okay, and also okay. So once again, we don't have like any additions here. So if we have these boundary conditions, then everything will be 0. So we need to change boundary conditions. Yes. So we need to consider this case I0, 0. Because this means that we don't have any items, and so our back is empty. So we cannot like put anything to it. So can we fill space of empty? I mean, it's we can have like so actually so actually for every number of elements, we also can, if we have an empty space, it doesn't matter how many elements do we have. Okay. So what is the time complexity of this algorithm? We because our recurrence relation, it works in constant time, so we need to only calculate how big the array in dynamic programming is. So we need to see what are limits of I, and these are from 0 to n, because we have to calculate, consider all items up to n, and also the size of j is from 0 to the maximal size. So this is m. So we need to fill this whole array. So the time complexity will be n times m. Okay, and if we come back to the original question, so what is the maximal size we can fit if we have a certain limit? Of course, d n m is this is true if we can like fit elements such that the whole back is filled. But sometimes this will be not possible, and we are asking for the maximal value. So we need to iterate over all values from all values of this form, and we need to take a maximal j, which is true. So we need to take maximum value j such that this is equal to 1. So after the standard dynamic programming, we need also to iterate through this array. Okay. Okay. So let's write down the actual program. Maybe we can write it here. Okay, so let's suppose that we have array D. This array will be array of bools. We have some maximum value of n. We have some maximum value of m. We also have n will be the number of items. We have some weights. It doesn't matter really if we index the array w from 0 to 1 or from 0 or from 1. So let's suppose that we actually go from, I don't know, let's go from 0, and we have value of m. Okay, so first of all, if you have a dynamic programming, you can do it both ways. You can write a recurrence function, which actually essentially is just re-implementing this recurrence relation into a function. But usually it's you can have a little bit faster programs if you write it in iterative way. So let's try to write it using iteration. So then we need to start from the boundary conditions. So we'll have two loops. One loop over all items, and the second loop over all possible j's. So one loop will be over all items, and the second loop will be over all possible values of j. Okay, and here in the lower loop, in the inner loop, we'll be calculating dij. Okay. So first of all, in the outer loop, we will have to consider all the cases when we have zero elements. So we will need another loop for j from 0 to m, and we need to put something here. So we'll need to consider all the cases when we have 0 elements. Okay, so what we have here, 0, almost 0. Because we have this case, but we also have this case. So we have, if we I is 0 and j is 0, we need to put 1. So we can just put here j equals to 0. So this condition will be true only if j is equal to 0, and then it will be just interpreted as 1. So, and if j is not 0, then we will have 0 here, and this is the case. Okay, so here we have our first boundary condition, and let's see what will happen next. So the second boundary condition we can put here. So let's go from 1 to n, and so this is just putting 1 here if we have an empty knapsack. Okay, and otherwise from the other values of j, we just have to implement this recurrence relation. Okay, so we first of all we can say that the dij is just di minus 1j, and additionally if this is the case that we need to make sure that we have a correct indexing in the array of w. So if this array is indexed from 1, we can just put we. If it's indexed from, so let's say that this is indexed from 1. If it will be indexed from 0, then we will need minus 1 here. Okay, so if this is smaller than j, we can just say that dij is di minus j minus w. Okay, this is just an OR operator. So we are taking OR from this guy and from this guy. Okay. And of course we need to put a loop here. I think I will be using mostly indentation to show the structure of the program. Okay, so this looks like a correct program, and the question is, can we simplify it somehow? Yes. So this is one idea is to use only one row of the dynamic programming array, so first of all, why it work, and the second, why do we need why would we need it? Okay. So the main idea is in the dynamic programming, if we have if you have some array, for instance, here we have like a rectangular array, and we can see what elements are field in this array. So if we want to fill the cell number on the ith row and jth column, we can see what other columns are, what other cells are we interested in. So, for instance, if we want to fill out this cell, we are interested in the cell which is in the row above. So in the row I-1. So we are interested in this cell. And also in the cell which is row above, but some number of columns to the left. So here we have some column j minus wi, and we are also interested in this element. So normally we use quadratic memory to store the whole array, but as you can see, we only use if we want to calculate another row, we only use values from the previous row. So the standard technique is to, if we want to have linear memory, so we will only store the two last rows of the array. But here we even can go further, and we can store only one row of information. And why is that? Well, the question, the thing is that here, if we ignore this additional case, and if we see only this line, so this line says, let's rewrite row I-1 into row I. So this is like just copying the information from the upper row to the lower row. And basically, we only need to update this lower row if this value holds and if this and actually if putting element I is profitable for us. So actually we can reuse our memory, and we can squeeze all of the information in just one row. So then we will have something like this. Then we will have only one row, which is, so let's say it will be dj from 0 to m. And what will happen then? We will have, if we want to fill out the jth element, considering that we are actually considering the I element number I, we will first need to copy the information from the previous row. But we will put all the rows in one place on memory. So actually we know that here we have the information about the previous row. So we do not need to do any copying. And then we need to see whether it's optimal for us to actually whether this cell is true. So whether this cell here, so this will be j minus wi, whether this is true or not. And actually we will only considering cells which are before the cell we are going to change. So this means that if we so this will be not as easy as it seems, because we cannot use this loop directly. Because if we use this loop, we will be going through the elements, and for instance, if we change this element and later in the array some element will try to refer to it, it will refer to the already changed value. So this is not good. But if we change the loop, so we will be going backwards, so from these elements to here, then this will not happen. So actually every time if we change element dj, all of the previous elements will have the information from the previous row. So actually this this will work. Okay, so this is it. We will write a program, a second version of our program here, but there's also one additional change we can do to this two-dimensional program, which will simplify it. So the question is, do we need this instruction? Okay, do we need this? Well, the answer is no and yes. No, we don't need it in this form, but we need to, because if we have like two-dimensional array, we need to fill out this this value. But we can fill it out. We can just copy it from the top row. So if we put j equals to 0 here, this line will be just line will be just copying the element on the 0th column from the previous row. And we know that in the first row on the 0th column we have 1. So actually this will be copying 1 downwards. So we don't need this. We don't need this line. Okay, so this is a little bit simpler. Okay, so let's write down the program which uses only one line. So so now our array will be only one dimensional. Okay, and the first loop does not change because we still need to initialize it from the case when we have no elements. Okay, and then we have another loop. So the loop structure here does not change, but then we need to go from j equals to m to. So we need to change the direction of the loop here. So we don't need any of this copying because we know that in this row, if we are here, then information in array D is just information from the previous row. So we only need to update here. So we need to put an if wi is less or equal to j. Yes, that's actually a good idea. We don't need actually here the this if. If we go with this loop a little bit earlier, so we need to satisfy that j is at least wi, so we can put it actually here. And then we don't need this if. And we only need this we only need to consider if the j minus we is true. So if this guy is true, then this guy is also true. Okay, and here, as for the answer, we used only the last row of the array, and here the last row is actually the only row. So we'll take the maximal j such that dj is equal to true. Okay, what's the time complexity of this program? Yeah, it's the same as previously, but the advantage of this program is it uses linear memory. So for instance, if it's easier to actually fit it into the cache of the processor. So probably it will be a little bit faster thanks from that, and also it's shorter than this program. We don't have additional ifs, which ifs are also if we can get rid of the if in the critical loop, it's also very good. So this program it's quite short and quite fast, and this is and this is like the good approach to the standard knapsack program. Okay, and actually this gives us a little more information because in the initial formulation we asked for the maximum amount of items we can fit into the bag of size m, but actually as a byproduct we calculated this array which says exactly for each sizes of the bag up to m whether we can fit elements which for this size, and this is and this is this row. The information is stored in this RID. So actually, we will call this knapsack structure. So this is the array which allows us to answer in constant time for every j. Do we have enough items to fill the space exactly of j? Okay, and now we will go through the different variations of this program, and we will see how to change our program to for these variations. Okay, so the first formulation of the knapsack is called so this original program is called 0-1 knapsack. So you can also only take one item from each kind. So what about if you have like unbounded numbers of items? So for each item you can take as many items as you want. So for instance, if we so let's write it here. So this will be unbounded knapsack. So for instance, if we have like our first case, the first example. So okay, so if you have unbounded knapsack, so you can take for each item you can take as many copies as you want. So this example is not very interesting because you can take as many ones as you want. So actually you can like fill every integer space possible. But if you have only these elements. So for instance, if m is equal, or let's say j, if j is equal to 4, is it possible to fill up? Yes, you can just take 2 and 2. But if j is equal to 3, you cannot do this. And if j is equal to, let's say 9, you can just take 2, 2 and 5. Okay. So how to solve the unbounded version? Yes. So this is like the yeah, we can go this way. So let's look at this loop here. So we said that we need to change the order of this loop from this this natural order here to this order, because we are only working in one row, and if when we go into order from 0 to m, we would be erasing information from the previous row, which is needed for the next cells. So actually, if we have like this cell dj here, so we would be, so we need so here we needed information in the previous cell, so we cannot lose this information. So we need to go from this direction. But we can think about what exactly we will be calculating if we would go from the normal direction. So what will happen if we go through here? So actually, this element j would be asking, okay, so what is the can we so we are asking, can we fill up the space of j using elements from 1 to I? And in order to do this, we are asking this this recurrence relation. So we ask whether we can fill out the smaller space, because we use the ith element, with elements from 1 to I minus 1. Okay, but if we want to calculate the unbounded version, we actually are asking here, what is the number, can we make fill the space of j minus wi with elements from 1 to I, because we still can use element number I. So if we go to this recurrence relation here, so this says, okay, if I want to use element I, either I don't use any element I at all, and then I have this this value, or I can use at least one element I. At least one, it means that I can use 1 or 2 or 3 more. So actually here, I can still use elements of size I. So this change will actually show us a recurrence relation from the unbounded version. And this change is exactly this, what will happen if we go through this direction in this array. Because now if we are considering element dj, the element dj minus wi was considered before. So actually in this row, it will have the information about row I. So for the unbounded version, we just have a loop from j equals to wi up to m. And Everything else stays the same in this program. Okay, any questions? Okay, so let's try to complicate it a little bit more. So what about bounded Knapsack? Because here we have two opposite possibilities. Either we can only take one element of each kind, and here we can take as many elements of each kind as we want. So what about the case when we have, for each type of element, we have the number of elements we can take. So let's call it bounded knapsack. And now for each item, we have two values. First of all, it's WI, and this is like the standard weight or size of the element. And we have also a bound of the numbers of elements. So we can use at most BI elements or BI items from type I. Okay, so one idea is very natural, although not very fast. If we have at most BI elements of type I, we can just like make BI copies of this element. So the one idea would be just make BI copies. So we will have like BI elements of the size WI. So we will have like so we have this number of items. So instead of n items, we will have sum of all copies, and we just run 0, 1 knapsack algorithm. So it's clear that this will work. It's not nothing special here. We'll just we're not using this like information that we have many items of the same size. We just throw it once and again. So actually, if we have this this program here, we would we can make another loop here. Yes, so we can make a loop here for, let's say, for x equals to 1, x smaller than bi. So for ith element, we just make a loop of size bi, and we are just iterating bi times putting elements of this size. But this is not very clever and not very fast, because if we say that the maximum number of copies is, let's say, b, so this algorithm we will run in time n times m times b. Okay, but it's not very clever. So we'd like to have something more fast. Okay, but let's try to push this this idea of making copies a little bit further, because the problem with this idea is like we are not taking advantage of the fact that we have many elements of the same size. This is one thing, and the second thing is we are like putting these elements, and actually we have many cases which we get the same answer. So, for instance, if we have like element like if you have 3 elements of the same size, so it doesn't matter if we put, for instance, the first. If you want to take, for instance, 2 elements. So if we want to take 2 items out of this 3, it doesn't matter if we take the first one and the second one, or the first one and the third one. It doesn't really matter. So one idea here is to actually not make copies which are of size 1, but make some more clever copies. And the idea is here, so maybe it's easier to understand this idea if we have like the number of copies which is a power of 2 minus 1. So let's see if we can use this number of copies. So it's like 7 or 15, or in general power of 2 minus 1. So if we want to so the basic idea is we want to be able to generate all the numbers from 0 to 2 to the k minus 1. Yes, because we don't know how many of these elements will be necessary in the optimal solution. So we need to make such copies that we can like take every possible number from 0 to 2 to the k minus 1. Okay, but if we see the power of 2 here, so maybe it's good to actually use the powers of 2. And the idea is to make copies which are actually of the size of powers of 2. So instead of, so here we make bi copies of elements of just of the size wi, and now we will make each copy will be like a block of several elements. So we will have one element which is of size wi, but we additionally will have an element of size 2 times wi and 4 times wi, and up to 2 to the power k minus 1 times wi. Okay, so as you can see, if we want to be able to take, for instance, x elements, so let's say that we want to take like 9 items. So taking 9 items of size B1 is essentially the same as taking 1 item of size wi and the second item of size 8 times wi. So taking 9 items of size wi is just essentially it's 9 times wi, and this is the same as taking this guy and this guy here, which is not included in the list one. So what it basically is, we are like we are writing this x in the binary form, and we just take these powers of 2, which has bits which has ones on the certain bits. So basically, if we have these copies, we can from these copies we can produce every possible variation of elements of WI, which was possible here. But here we like many times we have like the same possible size. Yes, because if we have 3 items, then it doesn't matter if we take this 2 or this 2. It will still be of size 2 times WI. And here we don't have like this flexibility, because if we want to take 3 items, so if x is equal to 3, then of course we need to take WI plus 2 WI, but so we don't have this flexibility, but we don't need it. And in fact, what we get only. Okay, so how many elements do we get here? Yes, we have here logarithmic numbers of elements. So essentially, the time complexity of this algorithm will be n times m times logarithm of b. So which is better, but we still need to consider one thing, because this works only if bi is equal to like to the power of 2 minus 1. So what if b1 is any number? Exactly. So let's say that bi is equal to this power of 2 plus some remainder, and this k is as big as possible. So it's like the biggest power of 2, which is smaller than bi. Then we additionally add this element wi times r. So, like the number of elements asymptotical does not change. It's still logarithm of b, and from these elements you can take any sum up to bi, and you cannot take any larger sum. Like the bi, this is the largest sum you can get from these elements. Okay, but we still have this logarithm here. Can we do better? Yeah. Okay. So this will be the idea we are going to present here. Okay. So the idea will be so actually the first idea would be a little bit naive, because we will we'll start again from this naive loop. We'll go through all the elements, and okay, yeah, okay,
If I want to catch 2k minus 2k exactly copies of the item,
yes,
I can what I should get. I would get all the potentials of y1, and I get the.
okay. So if bi is equal to 2 to the power of k, then r.
No, bi is 2k minus 1 plus r. This is fixed. But I need to get the best answer. I need to get exactly 2 to the k copies of bi. Yeah, I can get.
Okay, so
I will get all the. I will get all the copies that is that's multiplied by a 2 power.
so the
The plus 1 I can't get.
okay, so the idea is if you want to take something which is greater than 2 to the power k minus 1, so exactly 2 to the power, yes.
But let the
Okay,
2k
so you take this, you take this guy, okay, and then you need to take something, yeah. But here you have like you can take every possible sum from 1 to 2 to the power k minus 1. So if we, so your idea was that you need to take 2 to the 2 power of k, yes? So this is equal to
minus 1 plus 1.
r plus 2 to the yes, and r is actually greater than yes.
Not equal. If it is equal, I have no problem.
Okay,
If
but
it's equal to 1, I have no problem with this. The problem is if r is more than 1.
okay, but okay, so you need to take. So what exactly is bi?
I can do it. 1 plus r. But I need to get exactly 2 to the k copies of bi.
Okay, so
And my r is greater than 1.
okay, so
I can't achieve 2 to the k with this item.
okay, so you need to achieve 2 to the k. So this is exactly this, yes? So this guy, this r, is this guy, okay? And here you have 2 to the power of k minus r, which is, and r is greater than 1. So actually, this is as much as this. So actually, this sum can be achieved from all of the other guys, okay? Okay, so let's try to. Okay, so where are we? We are still on the bounded case, and we want a faster algorithm. So let's. Okay. Okay. So let's try this this idea. We'll try to We'll try to re-implement this algorithm So this this standard algorithm from the 0-1 knapsack, but instead of adding one element here, we also we always add one element here. We will try to add more elements, and let's see if it actually helps us. So let's start with this loop from I1. So we are considering every group of elements, and we are going. We are considering every possible and we are considering every possible possible size, of course, from the biggest one, because we do not want to erase our information. Okay, and what happened in this? Okay, so we, in the previous slide, we will just updating element dj, but it will be easier for us here to actually start from the element dj. So let's write something like this, and we say something like this. Okay, if we can achieve the subset of size j, then we can add some more elements to achieve another subsets. Okay, so so the idea is, if d of j is equal to true, then we can achieve another subsets. Which exactly? Well, let's say that we have at least one copy of element wi. Then of course element of size j plus wi is also achievable. Yes? But if we have more copies, then the subsequent elements are also achievable. So for instance, this one is also, and up to j plus bi times wi, as long as this is smaller or equal to m, because we don't need bigger elements. Okay, but so we can write a loop here, which goes from 1 to bi, which fills these elements. But of course, if we okay, so let's try it this way. So I will just rewrite it. So we have just a loop. So let's write it in a while loop. So let's say that k is equal to 1, and while k is smaller than bi, and j plus k times wi is smaller or equal to m, then we will update our array. So dj plus k times w1 is equal to 1, and we update the k. Okay? Okay, so what is the time complexity here? It's not better than this naive way, actually, because here we have loop over n, loop over m, and loop over at most b. So actually this is not very good, but here we can do one more observation. So suppose that we have this RID, and we know that element j, so here's dj, and this is equal to 1. So we can fill this guy. So here you have plus wi. So we can fill up these guys. Okay. So if these guys are zeros, we need to put ones here. But suppose that some guy is equal to 1. What happens then? Yes, exactly. If I have a guy equals to 1 here, so I can stop iterating now. Because all of these guys here, I don't need to fill them, because I will fill them starting from this guy. Yes, because it may, well, actually, once again, I don't need to fill them because I filled them before. Because as you can see, the loop goes from m minus, so the loop goes from here. So this guy was considered before. So this guy was 1 before. So actually this, when we were considering this guy, this was true. So we started filling all of these guys in this loop when we were considering this element. So if this guy is 1, these are also 1s.
Perfect integration with W with first 10. In this integration, public length. Second, public 5. Então, ao multiplicar by field, I repeating whatever is not valid.
I'm not sure whether I got the question. Okay, the idea behind this is that we can stop iterating here, okay? Because if this element was equal to 1, it was also equal to 1 when we were considering this this element in the previous loop. So actually, this loop here, when we are considering, okay, so we are considering item I. Okay, so if we are considering item I, so if we go to this element and we go here and here we have 1, okay? So let's think what was the value of this element when the loop of j was here. Could it be 0? If during the loop here, so this is j. If we are here and this guy is 0, so it must have been changed to 1 during one of these iterations. Okay, so maybe it was changed to 1 because of this element. But if it was changed to 1 because this element should have been 1 to be able to change this because of this, yes? Okay? So, but if this element was 1, we actually here could break the iterations here. Okay? So if this is the first place we break the iteration, all of these guys here, this one and this one, must be 0. Okay? So this means that they cannot put 1 in this element. So this element must have been 1 before this iteration. And if it was 1, it could put 1 in all the subsequent elements. And of course, the important fact is that it could put 1 at most for bi new elements, but of course this one also can put 1 at most b1, and this is shorter. So if we have 1 here, we can stop our iteration. So actually this goes. We have another condition here. So we must say and d j plus k times 1 is equal to 0. Okay, and it turns out that thanks to this this condition, the time complexity of this algorithm improves a lot. Sorry? No, you don't. So the question was, do we need to sort the items by bi? No, we can considering the items in any order. Okay, so what is the result of this condition on the time complexity of this algorithm? So let's see how many times we go into the while loop. So we are going into the while loop at least, well, n times m. So if we ignore the first run of the while loop, we would get n times m, because like this is the bound of this the number of times we go through this iteration. But then, if we have this condition that we are entering the loop only if when this cell is equal to 0, and in this loop we are changing this cell to 1, we can see that every time we go into the while loop, we are changing one cell in our array from 0 to 1. Okay? And what is the number of cells in the array? It's at most m. So actually, this is like the inner loops of while will go here at most m times. So this is like n times m plus m, which is essentially n times m. And this is the same complexity as we have in 0-1 knapsack and unbounded knapsack. So for the bounded case, we also have this low complexity, and the algorithm is no complicated. Okay. So one important fact here is that that our n times m algorithms are feasible because the size of the knapsack, so the size of m, is limited. So if we go through the whole theory, it's actually this is not quite polynomial algorithm because the size because it's dependent on the size of m and not logarithm of m. So if we so in the full general, if m is big, then we don't know any polynomial algorithm for the knapsack problem. It's in NP complete. But usually in the when we can use this dynamic programming, m is limited. But there are some cases when even for big M, we can invent some nice algorithms, and one example of this is when we have big M, but quite small elements. So if we would have a big knapsack and big elements, then the problem is NP complete, and we know only exponential algorithms for this. But if the size of the knapsack is big, but the elements are quite small, then we know also a polynomial algorithm. Okay, so let's suppose that which one should I? Okay, I think I can. Okay, so this is the case when we have big M and small wi. And let's say that we okay, and let's say that we have unbounded version. We have unbounded version, so we can take any element of we can take items of each size as many times as we want. Okay, so once again, there are some examples in which this is quite easy, regardless of how big M is. So once again, let's take our first example. So we have 3 elements of size 1, 2, and 5, and we can use as many items of each size as we want. Okay, so in this case, once again, we can take as many ones as we want. So for every size of M, we say that we can fill the space with this number of ones. So if we want to put, if you have M, then we just use M times the element of size 1. So this is easy case. But what if we don't have? What if we don't have this element of size 1? Okay, so for instance, if we have big M equals to, let's say M is equal to 10 to the power of 9. Okay, so the idea is that from some point every element, every size will be obtainable. So regardless of how big M is, and at some point everything will be obtainable, and use the argument of GCD. Well, actually, here's a little bit simpler argument, because we have element of size 2. So for instance, if M is equal to 10 to the power of 9, we can just use elements of 2, and we can use these numbers of these elements, and this works because this number is even. So for all even numbers, we can just use elements of size 2, and we are okay. But what about odd numbers? Well, it turns out that we need to use at least 1 5, because this is like the only odd number which we have. But if we use 1 5, then we can put again only elements of size 2. So actually we have two cases. Either we take only 2s, or we take 5, and then we can just 2s. So in this case, every element of size even size is reachable, and for elements for odd size, we can reach 5 and every element bigger. So as you say, there's a point in which from which we can use everything. After 5, we can use everything. So if M is greater than 5, then so let's say if J is greater than 1, then D odd from J is equal to 1. Else we can just calculate it with the limit of 5. So idea is the idea is to actually find where is this starting point after which we can take everything. Okay. And what about more complicated examples? So, for instance, if the smallest element would be 3. So then we can use the same idea. I mean, we can put as many elements of size 3 as we need. And then there's only a problem in which we have to we only need another elements when the size of J is not divisible by 3. And then we have two cases. Either the remainder is equal to 1 or the remainder is equal to 2. Okay? You wanted to... Uh-huh. Uh-huh. Mm-hmm. Yes, exactly. Mm-hmm. Yes. Yeah. So actually the sorry? Yeah, that's the idea. So the idea is so let's take the smallest element. So let's suppose that W1 is the smallest element of the smallest size of all the elements. So maybe I can I reuse this? I'm not sure. Okay, let's write it here. So V1 is the smallest element. So the idea is we would like to calculate the value T from T0 to TW1 minus 1, and Ti is the smallest size j which is obtainable, and j modulo W1 is equal to I. Because so for every remainder modulo W1, we would like to know the smallest size which we can obtain using all of the other elements than W1. If we know this, then we know that we can use Ti plus any number of not j but plus any number of elements of W1. So actually we can say that dj is equal to 1 if and only if j is greater than Tj modulo W1. Okay, so this will show when we actually write an algorithm for calculating t. It will show how much, because this algorithm, it will depend on the value of W1, and actually this is the only value which we're interested in. So this is the smallest value. So W1 should be quite small. We will see how small exactly in a minute. And other elements, it turns out that could be anything. Okay, but we will go to this in a minute. So actually, for answering the queries whether we can pack elements of size exactly j, we will use only this RITI. So actually, we don't need to fill this RIDJ. This could be just a function which queries this in constant time. So it just tests this this inequality. Okay, so the idea now is we need to calculate this RIT. Okay, and how do we do this? Well, first of all, we know some values of t. For instance, what is the value of t0? It's 0, because like the 0 is the smallest. The 0 has the remainder of wi equals to 0, and this is the smallest thing we can obtain. Yes, because we don't need any items to obtain the size of 0. So, for instance, we know that t0 is equal to 0. Okay, so how can we obtain other values? Well, actually, we need to see what are the other elements in the array. what are the other elements we can use? So for instance, let's say that we can use W2. So we can put one element of W2 into our knapsack, and this will show us some kind of obtainable value. So for instance, if we put only W2, this would mean that T of W2 modulo W1 must be smaller than W2. Yes, because this is the reminder for W1, and this is one way of putting elements to get this reminder. So we in the RIT we have the smallest obtainable values. So if we can obtain W2, this must be smaller. Well, and again we can do this for every possible element. So we can put like W3, but then we can also put 2 times W2 and so on. So it looks like we need to consider many cases here. But actually, if we see that we need to find some smallest value, which is taken by taking the subsequent elements, it turns out that this could be turned out into a graph problem. So we will considering a graph in which we will have W1 vertices. So we have vertices from 0, 1, 2, 3 up to W1 minus 1. So these vertices are the remainders of W1. So these vertices in the graph corresponds to elements of RIT. And then, okay, we have a graph, we have vertices, and we need some edges. So for edges, we will consider every possible element. So the idea is, so let's suppose that we can start from 0. So that means that we are in the case where we have some size with reminder of 0. And what happens if we add element of size W2? It will get we will get a reminder of W2 modulo W1. So we will have an edge to the vertex W2 modulo W1. So we will have an edge here, and this edge will have weight equal to the size of the element. And actually we will have edges from every vertex possible. We will have edges for every possible element. So for instance, from element equal to 1, we will have also edge of W2 to element W2 modulo W2 plus 1 modulo W1. So in general, if we have vertex I, and if we, and if we have some element K, so we will have an edge of weight WK to the vertex, which is I plus WK modulo W1. Okay, this is our graph. Okay, and can you see how can we use our graph to calculate the values in our RIT. Exactly. So we will find the length of the shortest paths starting from the vertex 0. So basically that. So what does it mean that we have some path from vertex 0 to some element? So for instance, we have our graph. We have here element 0, and we have some path to vertex I. So that means that if we take elements, let's say here's you have like W2, W3, once again W3. So that means that if you take element W2, element W3, and then element W3, you end up with the size which has a remainder I when divisible by W1. So this means that W2 plus W3 plus W3 modulo W1 is equal to I. And the length of this path, so the length of this path is W2, W3, W3, is actual the size of this subset. So I is the remainder of the size, and the length of the path is actual size of this subset. Okay, but we are considering here the shortest path, so the path with the minimal weight. And it turns out that this path of minimal weight is actually the minimal subset which can be obtained and which results in this which result in this remainder. So basically, what we are doing here, we are constructing a graph which has how many vertices the graph has? Number of vertices is W1. Number of edges it's n times W1, because for every vertex we have edge for every element. Actually, it's n minus 1 because we don't need the element of V1, but overall the size of the graph is n times W1. Okay, and to get the shortest path, we run Dijkstra algorithm of this graph. So the running time of so the running time, if we implement the Dijkstra using heaps, it will be n times W1 times logarithm of this value. Yes. So actually, this is a good remark that actually when you have edges, you see when you have two edges which has the same remainder from W1, then we'll go from vertex I, then we'll go to the same vertex. So essentially, you can keep only the shortest edge. So this shows us that we need for every vertex we need at most W1 edges. So actually, so essentially, this this can be written as the number of edges is minimum from n time minimum from n and w1 times w1, and of course it depends on how w1 is related to n. If w1 is like greater than n, then we take n here. But if w1 is smaller than n, we actually can use, we can have w1 squared here. And of course, this also goes through the through this. And there's also one more idea. I won't go deeper into this, but it turns out that for certain values of n and w1, it's even better to have a Dijkstra algorithm which don't use a heap, but it uses just Ri, and so the quadratic Dijkstra. It's for some versions of n and w1, it's better to use quadratic Dijkstra. Okay, and that's basically it. So we calculate this RIT, and I think this answers the question: what is the limit of the W1 in which this algorithm will be sensible? So basically, this should fit into time complexity. So if W1 is about I would say 100, is perfectly reasonable to use this algorithm. It's log of n times W1. Yeah. Yes. Okay. Okay, so we covered here 4 variants of the Knapsack problem, but one common thing about all these variants is that we talked about the problem in which every element has only weight or only size. And it turns out that we can make it more interesting if we introduce some additional parameters for the elements. So usually it is called some kind of cost. So here we were only interested whether we can take the elements in such a way that the total weight or total size of these elements is equal to j. But there's possibility that we have many subsets which satisfies this that have the same size, and we would like to take a subset which is in some sense optimal. So it has the largest or the smallest cost of the elements. So basically it means that for every element we do not only have the Wi, which is weight, we also have Ci, which is cost. And among, let's say that we are aiming for the minimal cost. So that means that for we would like to get, if we have some subset which is of size j, we would like to get a cost of a minimal cost of such subset. So, okay. Okay, so the idea is that we have knapsack with costs. So once again, our example, we have element 1, element 2, and element 5, and we have additional costs of these elements. So for instance, cost of element 1 will be 2, of element 2 will be 3, and for instance, this cost will be like 10. Okay, so if j is equal to, let's say 3. So can we obtain a subset of elements which total sum is equal to 3? Yes, we can. Still, we have element of size 1, so we can, for instance, take 1, 1, and 1. But the cost of this subset would be 3 times 2. 3 times 2, this is 6. And we have a subset which has a smaller cost. We just take 1 and 2. So then the cost is equal to 2 plus 3 is 5. So this is smaller. So let's say that we want to know the smallest cost of the obtainable subset. And let's say for simplicity, if the subset is not obtainable, the smallest cost is just infinity. So for instance, if j is equal to, let's say, well, here we have 1, so we can use everything. But if we would have like elements d1 equals to 2, d2 equals to 5, then if j is equal to, let's say, 1, then cost is equal to infinity, because we don't have any value here, any subset which has the weight sum of 1. Okay, and once again we can try to so we added like an additional dimension to the variants of Knapsack programs, because we can add costs to every variant we have so far. So let's start from the 0-1 Knapsack. So we want to calculate what is the smallest cost if we can take every element 0 or 1 time. So essentially, what we have here, we need to write down our recurrence relation one more. So basically, the array will be the same. We will be considering elements from 1 to I, and we will be considering the subset size of j. And now ij will be the minimal cost which can be obtainable. So again, we have two cases, and now we need to take the minimum of these cases. So one case is we don't take element I at all. Then we have just minimal cost when we consider elements from 1 to I minus 1. And the second case is when we are taking element I So if we are taking this element, we need to add a cost of this element to the minimal cost of elements which are smaller, and we only can do this if j is greater than equal of from wi. Okay, and once again we have boundary conditions. So one boundary condition is if we have 0 elements. So then what is the smallest cost we can achieve if we have 0 elements and a bag of size j? So if j is equal to 0, then the smallest cost is 0. And if j is positive, then it's infinity. So we can say that well, let's write down this way. If j is equal to 0, then the cost is 0, and otherwise the cost is infinite. Okay, and what about if you have 0 and all the so basically if we have empty bag, it's 0. So essentially this recurrence relation is pretty much the same as we have before. So all the algorithms for so it's easy to update this algorithm for 0.1 knapsack, which we have here, and here we have better version. But also this better version can be easily adapted to including this CI. So actually here we don't have or, we have here additional minimum. So we need to here we will put di j is equal to minimum of dij, and the value which we have here. So di minus j, I minus 1 and j minus we plus ci. Okay. And this will work also for the unbounded knapsack. So if we can take every element as many times as we want, because if you remember, the only difference between these algorithms was the order of this loop. So for the unbounded version, we go from m to 0. So it also works if we add cost. Okay, so what about bounded version? So what happens if we add cost here? Here we had 3 different algorithms. So the first one was the naive algorithm, in which we made just bi copies of each element. So now if we have bounded with cost, for bounded with cost we have 3 values for each element. We have weight, we have how many times we can use this element, and we also have cost. Okay, so for this naive version, when we just make copies, it's actually the same, because we just need to make copies, and each copy will have the same weight and will have the same it will have the same cost. So it doesn't really matter. So it still works in this in this time. Okay, so what about this second version? Does it still work? Yes, because once again, here we have like in each copy we have like bundled elements, like 2 elements, 4 elements in one bundle. So essentially, they have bigger weights, and of course they have the bigger costs. So this element will have cost ci, this element will have cost 2 times ci, and so on. So this algorithm also works. Okay. Does this algorithm work? So basically here we have a problem. Because what was the main assumption of this algorithm? The main assumption was that maybe I will rewrite it once more. So idea was that if we start from DJ and in this algorithm we started when this subset was obtainable, so it was 1 here. So in our case we need to start if this is obtainable, so if this is not equal to infinity. So if we know that this guy is obtainable, so we know that if we are adding wi, they also be obtainable. But now we are so as long as here you have like infinities, we are going to the next elements, and suppose here you have element which is not infinite. So we know that this element was obtainable before, but actually we cannot really stop iteration here because we don't know what is the optimal cost for this subset. Because it could be the case that adding this element wi, which result in a smaller cost here. So we will update the cost. So if we update the cost, it's actually we would need to go through all these elements because we do not know whether we will be updating cost or not. And this is the problem because like this breaks down like the main assumption for this algorithm, which was needed in order this algorithm to be fast. So actually, and we need in order to get this complexity, we will need something more clever. But it turned out that we can obtain this complexity even for costs. And I think now I can remove this part. Okay. Okay, so let's write the down our RID once again, and let's see how can we obtain element DJ when we want to add some elements of type I to smaller subsets. So what kind of possibilities do we have? So actually we will be considering this recurrence relation once again. So what kind of options do we have? First of all, we can take 0 elements. So we will have just di minus 1 j. So we don't make any elements of size wi. If we take 1 element, then we have this. So for 1 element, we have just j minus wi plus ci. So what if we take 2 elements? If we take 2 elements, then of course we have j minus 2 times wi plus 2 times ci. And this is this goes down up to the bi elements. So we take di minus 1 j minus bi times wi plus bi times ci. And from all those guys, we need to take a minimum. Of course, here we are assuming that all of these are greater or equal than 0 in order to consider each of the case. Okay, so how does it look on the picture? So on the picture, we'll consider elements which are on size j minus wi, j minus 2 wi, j minus 3 wi, and so on. And we need to first of all add costs which are in these elements, and every element is we add another value ci for this. So here we have two problems. Okay, so let's, for simplicity, suppose that ci is equal to 0. Well, that won't be quite useful, but we will see what is happening here. If ci's are equal to 0, then these parts of the equation are equal to 0. So then dj, to calculate dj, we only need to calculate this minimum from these parts of the array. So calculating this minimum is quite consuming, because we need to like consider all of the bi cases. But what if wi was equal to 1? What will happen then? Then our minimum, so if you want to calculate for this element j, then we will need to consider elements which are like in the common part of in the one part of the array. So here is like j minus 1, and here's like j minus bi. So what will happen if we, so suppose we calculated this for j, and now we want to calculate this for j plus 1. So if we calculate it for j plus 1, we will have to calculate them. So here, like, we take a minimum from this. We need to calculate the minimum from j minus bi plus 1 up to j. So as we can see, like the the parts of most of the parts of this arrays, when we calculate the minimum, overlap. So usually it's a good technique to take advantage of this, that we have like this overlapping calculations. So basically, what we need here, it's a structure which gives us, which allows us to calculate such minimums in the sliding window. Yes, so the idea is like we take a window which slides over our array, and we need to calculate the minimum inside this window. So there's a standard data structure for this. I will elaborate on this if we have enough time. But let's suppose that we have this structure. So we have a sliding window of the array, and we can calculate in constant time a minimum for this part of array for subsequent positions. Okay. So this is the case when Ci is equal to 0 and Wi is equal to 1. So maybe not very interesting. So we need to get rid of these two assumptions. So let's get rid of the assumptions that Wi is equal to 1. So what happens here? So we have this idea where this image when the elements are like they're not like continuous part of the array, but they're like empty spaces between them. So if we would like to calculate the j plus 1 from this, we see that we don't have any overlap here, because j plus 1 will be depend on this element, and this element. We have no overlap, but we have overlap with element d of j plus wi. Because if we want to calculate minimum for this guy, then we see we need this one, we need this one, and we need this one. So suppose that bi is equal to 3. So we only can use 3 elements. So here we have this overlap. We have these 3 elements actually overlap. So the idea is to use this sliding window technique, but not on every element of the array, but on every wi'th element of the array. So we will need wi sliding windows. So in our array, we take the element 0, w1, 2 times w1, 3 times w1, and so on. And these elements, like on these elements, we can make a sliding window for this idea. So this will be the one sliding window structure. Another sliding window we will use for elements 1, w1 plus 1, 2 w1 plus, well, it's wi, but doesn't matter, plus 1, and so on. So we will be having wi structures for sliding window. Okay. So this will help us to get rid of this assumption. So what about this assumption that Ci is equal to 0? This is a little bit harder, because now we need to consider what is happening in our sliding window. We not only want to slide our window, but we also want to add value to it. So basically, what is happening here? We are adding ci to the first element, 2 times ci to the next element, and so on. But let's see what is happening. What is happening here? So maybe I finally use another color. So for this edge, we are adding ci. For this edge, we are adding 2 times ci, and for this edge, we are adding 3 times ci. So the same goes for these guys, ci, 2 times ci, and 3 times ci. But suppose that we actually calculated the guys for dj. So actually, let's suppose that in this elements here, we already calculated d for j minus 3 times wi plus 3 ci. So let's suppose that these guys were actually calculated correctly for this guy. So we don't have this here. Okay, so what this guy needs? It needs dj plus ci. It needs dj minus, so another guy plus 2ci. So if here we have already ci, we need to add only 1 ci more. And for this guy, we already had 2 times ci, and we need 3 times ci. So we only need to add ci more. And this is that. So basically what is happening here, if we slide our window to the next guy, we are taking minimum from the next window, but we are adding ci to every element in the sliding window. So actually, we are adding ci to the resulting minimum. So, so essentially, if our sliding window structure allows us to add element from one side, remove element from other side, and add a constant value to all of the elements, and take a minimum, then we are pretty much done. So let's write down what operations we are needing from our sliding window. So essentially, we assumes that we have a structure which contains some elements, and we have operations on this structure. One operation is to add one number from to the right. So add value to the right, and the second operation is to remove. So actually, this is a little bit more general, because in the sliding window we are adding one element and removing at the same time removing one element from the second end. But actually we implemented the standard implementation of the structure allows us to do adds and removes separately, because we will implement it as a queue. So in the queue we can push element from at one side of the queue, and we can pop element from the second side of the queue. And this will be a structure which allows us to take a minimum of all the elements in the queue. So we also have get minimum function, and also for this to work, we also need a function to add. So this adds x to every element in the queue. So these are standard queue operations. This is additional operation of taking a minimum of all elements in the queue. And this is an additional operation of adding x to every element in the queue. Okay. So this is everything we need to in order to implement this bounded knapsack with costs. So okay, so I will look at the computer in order to get everything right. I think we can remove this part. And we have an assumption that every operation in this queue works in amortized constant time for every operation. Okay. And okay, so first of all, we will have so let's I like to call this a min queue. So the queue with the minimum. So let's suppose that we have this this kind of data structure. So we will need a queue for every value. We need at least wi queues. So let's suppose that. Okay, let's say that this is maximal of them. Okay, and first of all, we need to initialize our RID. So once again, we will have RID of size max m. Okay. So the initialization is easy. We just, if we don't have any items, we will have, if j is equal to 0, then we have 0. Otherwise, we will have some kind of infinity. Depending on what is like the maximal total size, this should be initialized accordingly. Okay, and then we will go and add elements one by one. Well, we will add types of elements one by one. Okay, and so we know that we will be using wi structures. It's easy. It's easier for us to actually have additional operation of clearing the structure because we will be reusing these structures which will which were defined here. So we'll be needing WI's such structures. So we say Q, J, clear. Okay. And now we will be considering each position J. We will be going from 0 to M because each position depends on the previously of positions of smaller size. So we will go for J equals to 0 to J to M, and we will be considering this this guy dj. So first of all, we need to take a minimum from the correct mean q. So actually, this let's say that the mean q0 operates on elements which have the remainder when divided by wi equals to 0. Q1 will operate the elements with remainder 1, and so on. So in order to get the correct q, we need to take the remainder from J. So actually, we say that. So let's say that q is just a q of number J modulo wi. It's just some kind of reference for this q. Okay, and we need to do several operations of this on this queue. We need to make a pop, we need to make a push, and we need to make add elements for this queue. As I have this in the program, it's okay. I'm not sure if this is the correct order, but we will see it. Okay, so first of all, we need to also consider the operations when we have like smaller number of elements available in the mean queue, because it's sometimes if the value J is close to the left border, then not necessarily all of BI elements will be in the queue. So we will be popping from the queue only if the size of the queue is at least B. So if the size of the queue is at least B, so we have already BI elements in the queue. We are popping the last element in order to make a room. So of course we need another operation. We need to have a size of the queue, but this also can be done in the constant time. Then we add value ci to every element of the queue, and we push the element dj, and then we can say that okay. Yeah. I think that I have this here wrong, but let's see what. Okay, one thing we should actually no. Because let's see what will happen here. We also need to consider a case when we have when we are not adding any element of size I. So this DJ is actually the previous the DJ from the previous row. So this is like from the row I minus 1. This guy, and this is also included in the minimal calculation of the DJ on the row of I. Okay, so actually on this min queue we need to have bi plus 1 elements. Yes, because this is bi. Here we have bi elements, and we also need another element for this. When we have the case, we are not taking any elements. So I think this should be something like that. That we are not we are removing elements if we have more than b. So if you have b plus 1 elements in the queue. Okay, so what is happening here? Okay, pop is just removing the last element from the queue. Next, we are, for the remaining elements in the queue, we are adding ci for all the elements. So this is this corresponds to adding ci for all the remaining elements. Then we are pushing another element to the queue. So we are actually pushing the old value of this guy when we are sliding a mirror window, and the new value of this guy is just a minimum of all the values in the queue. Okay, so this should work. Modulo plus or minus 1 somewhere. Okay, and what is the time complexity of this algorithm? It depends on time complexity of this structure, but let's suppose that all of these operations are done in amortized constant time. It's the n times m, because we have like n times n loop here, and all of this is done in constant time. So this is n times m. So we have this this complexity of bounded knapsack, but with additional costs. Okay. We have a little time, so maybe let's make a vote. Who knows this structure? Okay, not many. So let's try to write down how can we make this structure with constant time of all of the operations, and we will remove this. Okay, so it's easy to look at this on the picture. So we have a queue. So we have we'll be inserting elements from one side, and we'll be removing elements from the other side. So let's say that the size of these elements will be integers. So let's write. Let's make a picture, and the size of the let's say that the size of the these bars are the heights of these bars are just elements in the queue. So for instance, it will be like 3 to 1, for instance 5, 4, 3, 6, 5, something like this, or 4. Okay, so we are pushing from one side, we are popping from the other side. If we don't have any minimum, then this is like normal queue, and we know that we can implement a normal queue in such a way that push and pop is in constant time. We can just use queue from the C++ also. Okay, but now we have a minimum. We need to calculate the minimum value of the of all the elements. And it turns out that not every element already in this queue is an interesting element. Because let's see which elements can be actually a value of the minimum. Okay, so if we calculate the minimum of all these elements, we get 1. Because this is like the minimal element in the whole queue. But can we have 2? Well, as long as element 1 is in the queue, this 2 will not be a minimum for this queue. And actually, if we are popping from this from the left side, this element 2 will be popped before we pop element 1. So actually, as long as this element 2 is greater than this 1, its value is not needed in the queue. So this guy, and actually this guy is even greater than 1. So these guys will never again will be considered as a minimum in the queue. Okay, but what elements could be a minimum? So for instance, if we pop 1 from this queue, what element will be a minimum? 3. It will be 3. So 3 is also a candidate for the minimum in some future. But can 4 be a candidate for a minimum? No, because it will be popped before 3 will be popped, and 4 is greater than this. So actually 4 and 5 are bad candidates. And it turns out that when we pop 3, the next 4 will be the remaining candidate, and 6 will be never considered as the minimum of the queue. Okay, so the blue guys are 1, 3, and 4 are the guys which are ever be considered a minimum on the queue, and we don't need to store these values as long as we know that they are greater than the next minimum. And we can see that the elements of these guys which can be considered a minimum are strictly increasing. So what will happen here? So if we push some element which is strictly greater than the guy before, like for instance, if we push 6 or 7, then this guy will be another candidate for a minimum. But what happens if we push some element which will be smaller? For instance, what happens if we push 2? So this guy will be definitely a candidate for the minimum, but 4 and 3 no longer will be candidates because they are greater greater than 2. So the idea is that we will be maintaining only the list of these candidates. So we will be maintaining the list of candidates. So for instance, it will be 1, 3, 4. And when we get an element which is greater, like 5, we'll just append it to the list. And when we have an element which is smaller, for instance 2, we will remove from the back of the list elements which are greater than 2. Okay, if we have this list of candidates, how can we extract minimum? Yeah, this is the first position. So this is like the first element in the candidates list is the minimum. Okay, so the minimum will be in constant time, because this is just taking the first element in this list. The push will be in amortized constant time, because sometimes we just add new element. If it was 5, we just add it in constant time. Sometimes we have to remove some elements, which is more than constant time. But as you can see, each element which we are removing was added before. So the removal of this element will be amortized by addition of this element before. So push is also in constant time. What about pop? Well, the problem with the pop is that sometimes we will be popping elements which are on the candidates list, but sometimes we will be popping elements which are not. And actually, we need to track the number of these elements which are not on the list. So actually, on the list, we will have pairs. We will have pairs. The value of the candidate. So here we have value 1, value 3, value 4. So let's say that we don't have this 2. We don't have this 2, and the number of elements which are preceding this value. So here we have 2 elements bigger than 1 before 1. Another 2 elements bigger than 3 before 3, and 1 element bigger than 4 before 4. And when we want to do a pop, we just look at the number of these elements, and if this is positive, we just decrease it by 1. So we know that there are 2 elements bigger than the first candidate. So pop, we just decrease it. Once again, we can decrease it when we are removing this 2. And if this number is equal to 0, then we know that there are no elements before this candidate, so we can just remove this candidate from the list. So pop will be working in constant time as long as we have the operation of removing things from the beginning of the list. So actually, this list of pairs could be we can implement it as the normal list in C++, or we can use the deck, or we can use the deck data structure. This is the queue in which we can add elements at the front and at the back, and remove at the front and at the back. So we have like push back and push front, and also pop back and pop front, and all of this is done in constant time. So we can use this one to store this list of pairs. Okay, so we have push, which is done in constant time. We have pop, which is done in constant time. Minimum is also done in constant time. Size. Can we have size in constant time? Yeah, we just store the total number of elements in this array. So we store additional size and every push we increase the size, every pop we decrease the size. It's nothing special. Okay, so what about add? What about if we want to add a value to all of the elements in this queue? So as we can see, adding a value to all of these elements, the same value, doesn't change anything in the candidates. Every two values, which if the value was greater than other value before, it will be greater after this change. So it's essentially the same as adding the same value, let's say value 3, to all of the candidates in the list. But still, the list of the candidates could be long, so we cannot traverse all of these candidates in the list. But we know that we are adding the same number to all of the elements, so we can say, okay, we are apart from from this list, we have additional variable add, which stores an amount which we added to all of the elements. So then the operation of add will be just adding C to all of the elements in the list. But we need to take care of the push now, because push needs to take care that we know that every element in the list is increased by C. So if we want to push value X in the list, we cannot push just X, we need to push X minus C. So actually we are pushing X minus C because we have assumptions that every element which is on the list will be increased by C. So if we want to have an X on the list, we need to just push X minus C, and then we know that this will be, the real value of this element will be X minus C plus add, which is no minus C minus add. So the real value of element will be X minus add. This is what we pushed, plus add, and this is X. So that's how we make this add to all of the elements in constant time. So I think that's everything. Well, of course we have also a clear operation, but the clear operation is just we make we clear this list of the elements, and it's also in constant time. So we will get the bounded knapsack with costs in times n times m. And I think that will be everything for today. Well, for the lecture. Thank you very much for your attention, and we will meet at the contest.